It's my pleasure to introduce our next speaker, Dr. Janice Coen. Dr. Coen is a project scientist at the National Center for Atmospheric Research in Boulder, Colorado, NCAR, that I think is a very well-known and beautiful place. She received her BS in Engineering Physics from Grove City College and MS and PhD from University of Chicago, which of course Argonne is associated with. Her interests are investigating wildlife fire behavior and its interactions with weather using computer simulation models and by analyzing infrared imagery of wildland fires. She's developed two coupled models for both climate prediction, or rather weather prediction, and wildfire fire behavior models that are in widespread use in the research community and transform the way people interpret fire behavior. I'm really looking forward to your talk, Dr. Coen.
Thank you. Well, good morning. I have a topic that I hope will warm everyone up in this snowy weather. I am a numerical weather prediction scientist by trade, but I became interested in wildfires around 20 years ago when we started connecting fire behavior to our atmospheric models. And I'll be discussing some of the work since then, where it is now, the trends we're looking at, and the sort of data streams we're pulling in now, and how this all connects to supercomputing. Well, first I wanted to touch upon a topic which has been gripping the news over the past week, very surprising, shocking a lot of people. Of course, I'm talking about the fires in Appalachia, not the election. We're not going there. These fires have been burning in western North Carolina. They're really surprising a lot of people, and they're making descriptions likening them to western wildfires, behaving in ways they've never seen in that area, and causing a lot of destruction. That's very unusual. Most of our fires are limited to the western US, at least the big ones. Let's look at wildfires by the numbers. You might be surprised to learn that overall 97% of wildland fires are extinguished under 100 acres. So only a very few percent are the ones that you read about on the news and cause the most destruction. In fact, 80 to 96% of the area burned is due to the very largest of fires. And in the past decade or so, people, I'm quoting Jerry Williams, who's a former director of fire and aviation management for the Forest Service, describes the emergence of megafires, a new type of wildfire. These are exceptional in terms of the size, severity, or the cost, or the impacts they've had. They've been noted in countries worldwide and have very high impact on communities. Some of the examples, one of the most notable in the US, of course, was the Oakland Hills fire, which in 2014 dollars would be a cost of over $4 billion. So when you read about fires in the news, you hear terms that we're seeing unprecedented fire behavior we've never seen before. That it's unpredictable. It's beyond what our models can reproduce. It's just not like fire behavior used to be. So some people are raising the issues, is fire behavior entering a new regime because of climate change, human building in the wildland-urban interface, and drought and so forth. Well, my research has looked at what's going on inside fires, how we can understand what they're doing and predict what they're going to do. If you look at it as a phenomena, what we see within wildland fires are fire whirls or fire tornadoes. I have some pictures here. Horizontal roll vortices, fire winds that are within the fire that are 10 times stronger than the ambient wind speeds. Bursts of flame that shoot ahead of the fire line, much like a flamethrower at over 100 miles per hour. Blow-ups and firestorms. Pyrocumulus is what we call clouds that form over fires. These are produced from the moisture within the fire, it's released by the fire itself. And when I look at this from a meteorologist, we see a lot of these phenomena are very familiar to us. We have analogous phenomena within weather, for example, tornadoes. And it became clear to us when we started this research about 20 years ago that these phenomena all resulted from dynamic interactions between the weather, which we thought we'd do something about, and the fire. As a result, it's become clear that these phenomena, which have important impacts for firefighter safety, are beyond what a human can integrate in their head, and that the simple operational tools people are using now aren't keeping up to this complexity, and some advanced tools are needed. They're particularly the current tools are particularly inadequate in a few conditions that I'd like to point out. One is what the firefighters call plume-driven fires. These are where the dynamics within the fire are created by the energy released by the fire itself, not driven by the ambient winds. Another complex situation, which is common in Colorado, is when the fire behavior is driven by mountain airflows. These can be really complicated and vary valley to valley. And these occur at scales much finer than current numerical weather prediction models can warn people about. And there's other conditions like cloud gust fronts, when clouds rain into the boundary layer that evaporates and creates an outflow, which might overtake a fire and change the direction it's spreading, and increase the intensity, and these have caused a number of firefighter fatalities. Other examples are fire whirls, backfires, chimney effects. All these things are interaction effects between the fire and the environment that we don't represent with our current models. So I think how this connects to supercomputing, and thanks to David for inviting me, is this became a computational science, statistics, supercomputing problem through these issues. First of all, we might have many simultaneous ignitions. Lightning strikes, you might have several thousand for each particular fire, and which ones are going to become wildfires. Any of these could become the big one, which burns 100,000 acres, but we know from history that only a few % get above 100 acres. So which one is it going to be? More complex computational fluid dynamics models are needed, increasing the computational complexity, particularly in critical situations. Like I pointed out in the previous slide, we need very high resolution in our atmospheric models at hundreds of meters. This is more than an order of magnitude finer than our national weather forecast models run currently. And we need to incorporate those fire-induced winds, which can be important. And we also have the issue of rapid error growth in these fine-scale models. So how do we predict out into the future for an event that might go on for 3 weeks or several months? Another issue is we might have many simultaneous fires going on in a region. We have limited resources, both in suppression and probably computational aspect as well. I'd like to know about the uncertainty of our simulations. So normally how we do that in weather prediction is to use ensembles of simulations to represent the uncertainty in our models. But again, if we have hundreds of fires and we want to model each of them and we want to do hundreds of simulations of each, that's getting to be a big problem. And meanwhile, we have a growing number of data streams and measurement platforms that I'll describe in a moment. So if we were to look at what's going on across the United States at one time, this is a map even from April showing you the ignitions that are being detected by satellites. The ones that have been present for a couple days are in yellow, the most recent ones are in red. And these are collected and displayed at the Remote Sensing Application Center here in Salt Lake. So the type of models we have, they might be very simple. If 2 firefighters show up at a new fire with their truck and a couple shovels, there's probably not going to be any modeling going on at all. They're going to be using their experience and intuition. Historically, some models are still around. These are algorithms that relate how fast that rate of spread of the leading edge of the fire is going to go as a function of the local terrain slope, fuel properties, and how fast the wind is blowing. That would be calculating the rate of spread at a point. There are two-dimensional applications of such models. Those model how a fire spreads at the surface, and those usually use estimates of wind speed from local weather stations. In terms of computational models, at this point, you really have to make a choice. I work with models that take care of the weather in complexity, but we treat the fire rather simply, because we're looking at large-scale fire behavior. Those might incorporate the weather directly into the model, or as I do, integrate the weather with the fire behavior so that the fire behavior can in turn change the weather. Other people work with even more complex fine-scale models. These are computational fluid dynamics models, not weather models, with parameterized combustion. And they'd be looking, when they say large scale, they're talking about a box that's a meter on a side. So they're looking at combustion at centimeter scale. There's no full combustion treatment, direct numerical simulation right now for modeling things totally, so we're all doing some kind of parameterization. And if you look from top to bottom, these are increasing complexity and computational cost. Again, this yellow box is the area that I work in. So what we do, we connect our numerical weather prediction model to a fire behavior model. And those are connected so that the weather, as it's varying in space and time, is directing where the fire goes. And as the fire burns through fuel, it releases heat and water in the form of a gas into the atmosphere, which makes it buoyant and want to rise and changes the winds around the fire. So these are two-way coupled. So the overarching goals of my research program is to model the evolution, distinctive characteristics, and turning points, things when things change in large wildland fire events in a variety of atmospheric conditions. And we want to capture their time-varying extent, shape phenomena, and fire effects. And also to monitor and predict such properties within operationally defined accuracy metrics throughout their lifetimes. And the first one is kind of a research thrust, and the second one is trying to make these models more practical. So the model I use is called the COFFEE model, Coupled Atmosphere Wildland Fire Environment, combines a numerical weather prediction and a wildland fire component. Where are you? There you are. So there's some basic properties that we looked at first, like why wildland fires almost always spread in an elliptical shape. And it turns out even if you start a fire in a line with a wind pushing it from behind, it bows forward into this elliptical or bow shape. That's because as the fire starts releasing heat into the atmosphere, it rises and pulls air in at its base, and it pulls the fire line closest to it faster. So the fire spreads faster under this convective column. And you'll see the fire spread into this bow shape. But along the edge, you'll see a little perturbation start. When we did this might have been 32-bit round-off error, but in the real world, it could easily be an extra fuel pocket. So the fire burns a little more intensely there, creates a little more heat, a little stronger updraft. So when it's tilted and twisted into the vertical, you get fire vortices along the edge of a fire, and they can travel along the edge of the fire to the leading edge of the fire where they can interact and burst forward, creating this erratic behavior. I won't go into this in detail. The model I used is, we have many numerical weather prediction models. This one was built, started being built in the 70s, and it was built for fine-scale simulation of airflow in very complex terrain, so hundreds of meters. That's kind of a custom bespoke model for those applications, such as windstorms, seeding of clouds in the mountains, what else did we do with it? Cloud entrainment studies, very fine scale work. And the fire behavior component First, you have to represent this interface between the burning area and the unburned fuel, track how it spreads with time, calculate the heat that's released as it starts fuel on fire. Once fuel is ignited, it doesn't burn instantly, but it releases heat over time. And fuels like grass release heat rapidly, but logs and larger fuels take time, and they release heat slowly over time, and that affects the fire behavior. And if there's enough heat and a tree above it, the fire can transition into the canopy, where we call it a crown fire, and those can spread much faster. So how did this work in application to a real case? First, we're modeling weather over a very large region, perhaps the western US. And we use grid refinement, both in the vertical and the horizontal, to telescope in to model airflow in perhaps a particular mountain valley where a wildland fire is at much finer resolution. So the types of input data we have, if we're looking at a past event, we have gridded atmospheric analyses, which is a model integrated version of all the data we collected about the atmosphere from satellite surface stations and many other sources. If we're looking into the future, then we would initialize our model and give it later boundary conditions from another coarser model, perhaps a global model. Another sort of data is terrain data, which we now have all over the world at fine resolution. And we need some information about how the fuels vary across the landscape. When I first started this 20-some years ago, we didn't have those databases, but you had to track down the fire behavior analyst and get a paper map under his desk and digitize it and try to make sense out of that. But now we have baseline databases for at least the country, and you can generate them for anywhere in the world. So one case we looked at was the High Park fire outside Fort Collins, Colorado. It was during a long, severe drought, and it occurred during an unseasonal June windstorm. Most of our windstorms occur in December and January, but these overlapped and created conditions for rapid fire growth. I shouldn't even call it unusual, because we've had a succession of most destructive fires in Colorado history, each outdoing each other year after year, and they all seem to come when drought is overlapped by a June windstorm. In fact, the Hayman fire, which was previously the most destructive, started on the same day 10 years earlier. So this is kind of one of our first big wildfire events, and it, of course, was started by curiosity. I saw this first fire map of the fire extent, and I couldn't understand why it had behaved the way it does. Because I've been in Colorado a long time. We know windstorms blow from west to east, so why didn't the fire just burn east? Instead, it looked like it went to the north. But when you look at the fine-scale winds, things like that become obvious. So here's the sequence we're going to look at. The fire spread first to the north, before going east. And I'm going to show you a cross-section through this magenta line here. The ignition point is about midway through it. So if we look through that line and we look at the atmosphere going on above, what we see is gravity wave breaking. This is when you get heavy, stable air near the surface, lifted up over the Rocky Mountains, finds itself heavier than the air around it, so it wants to go back down, and it starts a wave motion. Under certain conditions, when there's enough wind shear, that is, the wind's increasing with height and the right stability and the right terrain aspect ratio, you can create gravity waves that overturn and break. And when that happens, they bring a lot of strong, high-energy air down to the surface, creating the 100-mile-hour winds we experience down in Boulder. So, okay, go. So if we look at the winds through that cross-section, faster winds are in red and brown, slower winds, stagnant, are in white and low in purple. So this is where the ignition was. This starts very close to the point where the fire picked up under the windstorm. So during the early period of the fire, even though there are winds blowing at 100 miles per hour on the mountaintop next to it, the winds blowing over the fire are almost stagnant in this plane. It's because there's a dome of pressure over it protecting it from these winds. But you'd see what we experience downstream on the Front Range. We get these periods of gusts where we get winds that might be up to 100 miles per hour. So as the fire unfolds, the windstorm creeps further and further down the mountain range, spreading the fire to the east. So that's what's going on in the air above the fire. So let's look at how it impacted fire behavior. This is that same sequence. We're looking at the surface. So the vectors are pointing downwind. Longer arrows are faster winds. I'm going to show you a color contour, and that's showing you the intensity of fire. The more intensely burning regions of the fire are in yellow and white. Less intensely burning regions are in darker red. So during the early period of the fire, you can see the fire is sheltered from these very strong windstorm winds on the peaks just upwind of it. And instead, it's getting these rather weak gusts coming off the Mummy Range outside Estes Park to the south. So as time goes on, the synoptic situation is changing, and the orientation of the winds with the mountain is changing, and the windstorm winds are shifting a little to the east, and some of them are beginning to impact the fire as it creeps up this intermediate ridge. And now they're being exposed to the winds, and it starts to turn east and spread rapidly. We also model the smoke from the fire as it consumes fuel. A certain percentage of that is released into the atmosphere as smoke. And with this type of model, we can show where the smoke is transported, but in comparison to current air quality models, the intensity of the fire determines how deeply it penetrates into the atmosphere. Because if it gets into the upper atmosphere, it could travel thousands of miles. So in terms of the computational cost of this, which I guess is what would be on everyone's mind, I always give everyone this squishy answer of it depends. Really, to capture the phenomena that's going on, the resolution varies. And for a situation like that, we have to model the atmospheric airflow at hundreds of meters and very fine time steps. In other situations, it could be very coarse. This is a plot that I was actually trying to test the impact of beetle kill. People were saying, oh, beetle kill is going to make the fire burn much faster. So I was testing out the impact of beetle kill, which is appears to fire as a very low fuel moisture in the canopy above the fire. So this is a collection of simulations that we're using only 4 nested domains and varying those fuel moistures. And it turns out, as other experiments have since verified, the fuel moisture, which everybody thinks is making fires huge, the effect of drought, it isn't that much compared to other factors. So the beetle kill doesn't have much impact at all on the fire extent. But what does, this was the 5-domain simulation at 123 meters. These were done only nesting to 370. We really need to capture that fine scale resolution and the wave breaking to represent how a fire unfolds. And that makes our computational cost a lot higher. If we look at another case, Yarnell Hill fire in 2013, this was a 19 firefighter fatality fire that occurred on the last day of June. So it's in Arizona, so the sun is really beating down on the ground and stirring up eddies. But what is also happening is there's a tongue of moisture coming over the northwestern U.S., circling around and approaching this area from the northeast. And as this tongue of mid-level moisture comes across mountains and gets lifted up, it creates thunderstorms, which rain into the boundary layer and evaporate. But as it comes over this successive range of mountains, it kicks off more thunderstorms. So if I show you how this unfolded. So the fatality report shows how the fire unfolded during this day. It was very small. It had been going on for several days. It spread first to the north before changing to the east. And then when the thunderstorm wind gusts hit it from the northeast corner, drove it suddenly to the southwest. So in our simulation to the right, this is the innermost domain. The sun is beating down on the surface, creating these boundary layer eddies, which are shown in the vibration of the winds. The fire spread first to the north, and it encountered this gap flow between two low mountain ridges, which is what turned it to the east. But meanwhile, as I said, this tongue of moisture is coming over the mountains, creating thunderstorms and raining into the dry boundary layer. And when that happens, it evaporates, develops a very cold flow at the surface, which enters from the northeast corner of our domain, impacts our fire, changes the direction it spreads, and drove it to the southwest over where the firefighters were sheltered. In terms of timing, we caught it almost exactly right when it encountered the fire, and it was within 15 minutes of when it drove the fire over the firefighters. So those are two examples of those situations where coupled models are very important, when the weather is changing rapidly and when we need to represent complex mountain flows. This was another important event, the King Megafire in the northern Sierras. It occurred, just for location, this is Lake Tahoe. The fire area was a little to the west of it. So this had been burning for a couple days, and it was spreading slowly. There were diurnal winds, but they were really pretty weak, so people weren't anticipating rapid fire growth. But during one afternoon, which to all appearances seemed like the days before, the fire grew rapidly, 25 kilometers up the Rubicon River Valley. But the operational models that were used didn't capture that at all, and people couldn't understand why it had occurred. So on the left is the mapped evolution of the fire during this afternoon, and on the right is a simulation. So we started the fire in progress with some satellite data I'll describe in a moment. At first it spreads over this gently rolling terrain, and as it enters the Rubicon River Valley, well, first you'll see a lot of fingers along the edge. Each of those has a convective column over it. It's pretty interesting. You'll see a bunch of smoke columns in pictures of the event. As it enters the Rubicon River Valley, which is slanted upwards to the right, it starts releasing a lot of heat, and a plume pulls the fire faster up the Rubicon River Valley. You'd see some really strong winds in there. And as this unfolds, I'll just let you watch. It spreads rapidly up the river valley and stops at approximately the right time at Hellhole Reservoir. So at this point in time, the large-scale weather is changing. It's changing to easterlies, and it's becoming moister, and that cut the fire behavior off. But people couldn't understand this before, but what we're able to capture with the coupled models is that we're resolving these really fine-scale circulations. There was a flow up the Rubicon Valley, which you don't see in those weather stations, which could be several miles apart. And we're also capturing the feedback between the fire and the atmosphere. So this is interesting. People were attributing this fire to, it must be the drought. It must be the fuel accumulation from years of fire suppression, but really it was this fine-scale meteorology and the fire feedbacks that contributed to the megafire. So one of my research thrusts is trying to convince people that we're basing a lot of policy on models that aren't really capturing what's going on. So we've done this sort of simulation in dozens of cases. I've got some listed there. Historically, it's been a problem to gather verification data because we never had maps of how the fire was evolving with time. In one case, we had a research aircraft which gave us some airborne fire mapping data, but that was kind of an exception. So validation has always been a problem. Now when we want to look at fires as a forecasting challenge, so that was reproducing fires in the past. Now we want to know how are they going to behave in the future. This has always been an obstacle because of these following factors. One thing is that following a lightning strike, a fire could smolder for several days without growing until dry, windy weather occurs, much like the High Park fire. And then it could grow like gangbusters for several days, and then there would be a lull, and it would just sit and putter, and then the winds would pick up, and it would grow again. So an individual fire could go on for 3 weeks, or in Alaska, it could go on for several months until snow puts it out. At the same time, our weather forecast skill deteriorates with time. You know this instinctively because if we give you a forecast for tomorrow, you can have a lot of confidence in it. For 3 days out, you're a little suspicious, and if you listen to what we tell you a week out, you know we're out to lunch. You don't have much confidence in that at all. But particularly with these fine-scale models, our skill might be only good for a day or so. And that's a problem because we're trying to model an event that's going to go on for 3 weeks. We can't also foresee everything with our model because those firefighters are out there dumping water on the fire and digging lines, altering its natural progression that we're modeling. And there's some processes going on, such as spotting. Here's a picture in the lower right, and that's where the fire is lofting burning embers up into the air above it, and it could start a new fire miles ahead of the original fire. And we could look at it probabilistic where those going to be, but deterministically where one ember is going to land and start a new fire, that's probably beyond our capabilities. So as a forecasting challenge, this has always been an obstacle. Until a few years ago, we started getting data from a new source. Here's what we had on the right and left over the past decade from the MODIS sensor. This is a satellite-based infrared sensor, and this is what it would show you about a fire. You'd see these blocks of heat, but it was really hard to see where the outline was. How this new sensor would see this fire, this is a fire in Brazil, is in the center, where we can almost get 9 pixels within what we had before. So that can clearly delineate a fire outline and also might give us an earlier detection. This is the VIIRS sensor. So now this is routinely mapping fires across the world and at mid-latitudes at least twice a day. And this has been a huge benefit to us. We could not only integrate that data in our models, but now we have validation data at least twice a day for fires wherever we might want to examine them. So we use it for initialization and verification. How we do that, we start our numerical weather prediction model running, and when we have an observation, we plunk that fire in the model already in progress. So we're inputting the extent of the fire in a running model, and we allow it to go on from there, and then we can validate it against the next observation. So we realized that this was an important step, and what it would allow is us to forecast fires throughout their lifetime. So how we would do that, this is the Little Bear Fire in New Mexico, and a sequence of VIIRS observations are outlined in purple. So from top to bottom, these are a sequence of simulations, and how each simulation evolves with time goes to the right. So this is our first detection. If we allow that simulation to evolve, at 12 hours, it compares pretty well with what was observed at that time. At 24 hours, well, it has the extent right, but it had too much growth to the north and the south. And at 36 hours, our simulation is not surprisingly out to lunch. But that doesn't have to be the end of the story, because 12 hours from now, we're going to get another observation. And we can have a fresh simulation going and allow that to evolve, which is good for, at 12 hours, really good. And at 24 hours, pretty good as well, and so forth. So using this weather forecasting technique, we call it cycling, that is starting a sequence of simulations with a fresh state of the atmosphere and fresh fire observations. We realized we could simulate fires from the time they were first detected until they were extinguished and no longer detectable. But just in case, we were pretty happy. We thought we had it solved, but no. Never works out like that, right? We have some current research areas that are going to take us over the next hurdles, and those rely on better and more use of remote sensing fire and fuel data, closer integration between model and data, and some data mining approaches to really specific complex processes. So what if everything didn't go perfectly? Things that could go wrong is we could be in a weather regime that's particularly unpredictable. For example, predicting where clouds are going to form. We're not really good at that, and we might only be good a few hours into the future. And the 12-hourly data might not be enough to keep us in a good, skillful forecast. Our fire detection data might be missing for a variety of reasons. The fire might be obscured by clouds, instrument problems, sun glint, our viewing angle might not be good enough to give us a good look at the fire. But there's also some other opportunities that arise. When we get a satellite observation, we might also be able to, it's doing laps around the Earth. We might get another look at it from a different perspective. And there's also additional sensors and data sources that might help us out. One of those is the Landsat 8 satellite. It has a fire detection product, and it's at 30 meters. So the trade-off with satellites is you can have it at higher resolution, but you're only going to get an observation much less frequently. So we get 30 meters instead of 370 meters data, but we only get it every 16 days. But that might be a time that's really helpful to us. There's some other instrumentation which is coming online, both in a research and a private sector sense. We're getting people contacting us with UAVs that have infrared sensors. This is from In Situ. They're looking at the Paradise Fire with a very small UAV of a 10-foot wingspan. But there's also been some research going on over the past decade from NASA, the Predator-class drone, that they've had some multispectral imagery sending back data on fires. And these are additional sensors, and compared to the satellite, which is going to come at a fixed schedule, these can be directed, but everybody's been trying to figure out how to work them into the firefighting operations, which is really the biggest problem, rather than what can we do with the data. So in terms of the orbital track, like I mentioned, VIIRS is on the Suomi MPP satellite, and it's doing a polar orbit. And if your fire is here in North America, you might not just get 2 observations today, you might get 4 or even 6, because when it's going north, you might get a good look to the west, but also when it's coming down from the north, you might also get an angle that's favorable and give you another observation. So what does that do for you? If we apply that to a case, this is the Canyon Creek Complex. Just a bit of background, it was started by a thunderstorm that occurred during the night, and there were gabillions of lightning strikes, of which 12 picked up, and people started jumping on them right away, but 2 escaped initial attack. And a few days later, when wind shift came, the fire spread 34,000 acres, most destructive fire in Oregon history, and then another wind shift drove it to the southeast. But how would this have been different with this new sort of data and modeling paradigm? So the thunderstorm happened during the night. We had a number of lightning strikes. It turns out that Landsat came late that next morning, and we got an observation of lightning strikes at 11:43, and then the first VIIRS observation, 12:53, and the normal afternoon one at 2:30. So if you're thinking, when could I start modeling this fire, telling people what it's going to do, helping out, you don't have to wait till 2:30. You have 2 observations before that. And with that, you can start some simulations and perhaps enable informed action. So we did some simulations of that case, and we looked at all the data available. It turns out these additional sensors would have enabled 3 extra simulations and allow people to get going on it several hours earlier. Which might improve our forecasts and allow us to do more forecasts, keeping them more up to date. So another sort of another sort of use of data that we're using in the modeling, because we want to model them better, but we also want to predict detect them sooner. So we're using lightning detection data from the National Lightning Detection Network. Here's a picture of the strikes during the High Park fire, the simulation I showed you earlier. Thousands of them in the area of the fire, and one of them started the ignition that picked up and burned 80,000 acres. What we're doing with it is not relying on that active fire detection threshold that we use for the world. Okay, so your satellite active detection product, you have to come up with one product that works everywhere in the world. If it's too sensitive, you're going to pick up some false alarms, like some hot factories in China, and there's some other notable, like oil wells, some notable objects. But if it's too not sensitive enough, you miss fire, so you have to make a compromise. But the thing is, when you know there's a fire in the area, and this lightning detection, many of our western fires are started by lightning, that would let you look in that data perhaps with less rigor, because you know there might be a fire in there. You don't have to apply this algorithm everywhere, and you can pick up fires perhaps earlier. When we looked at that in terms of 9 large, just as a sample, 9 large 2015 fires that were reported ignited by lightning, our results were mixed. We found 4 that this algorithm wouldn't have improved. We found 4 that were impacted by clouds that we couldn't do anything about. But there was one, a 90,000 acre fire in Idaho, that we would have found 36 hours earlier. So I don't know if it's going to make a big game changer, but in some fires, if you could detect a fire 36 hours earlier, that gives you a lot more time to get on it and put it out. We've done some work remote sensing of fuel properties. Won't get into it here, but we have these spatial categorical fuel data, and what we're trying to do is develop algorithms that, so that we can get our fuel information purely from remote sensing. Right now we rely on forest inventory data, so you always have to have people out there, boots on the ground, measuring and cutting, and that's very labor intensive. But what if we could do it all from airborne or space platforms? So we developed these algorithms to develop this fuel data. In one place where we had the data pre-fire and after fire was the King Fire. And that's kind of a weird, messed up area because there's previous fire scars, there's lots of harvesting and replanting, so it's really kind of a messed up ecosystem. So what we found using these mapping data is we could do a much better job of the fuel data. And it had some impact on our simulated fire spread, but it really had a big impact on how we modeled burn severity. And that's really important because a lot of policy goes into managing these ecosystems. And with the more quantitative data from remote sensing, we could do a much better job on that. Okay, one last thing. We've developed some data mining techniques because there are some ecosystems such as fire spread and chaparral that our relationships that we're using in the models are really very crummy. So people are trying to figure out how fast a fire is going to burn in these fuel conditions in the laboratory, but that's not representative. And it's really hard to get fires, prescribed fires, to burn in chaparral. So what we're using is landscape scale airborne data where we fly over fires with high-speed imagery and watching how that fire evolves. And with information that I can extract on the winds within the fire and very high resolution geospatial data on the fuel properties, we're going to extract these relationships from the airborne data itself. And that's very exciting because this is one of those big unknowns in a very important fire regime. So we have some research projects that are making this leap from research to applications. Most of them are funded by the NASA Applied Sciences. These are coupled weather fire projects. I have one, and there's another working with a WRF-based model. UC San Diego is developing a fire prediction product, relying much more closely on their high-speed the high density weather network in Southern California, and my organization has a contract with the state of Colorado to transition the type of modeling I've been doing into operations. So in summary here, we're using this new technology, including advanced computational models, and it's starting to enter practice. Supercomputing is a really important component to this, but some of the other trends that are going on is more integration of the remote sensing data, more closer relationships between the model and data, and using new computational science paradigms like dynamic data-driven application systems and data mining to make the most use of what we have. So I'd like to acknowledge my sponsors, the National Science Foundation, NASA, and FEMA, and I thank you for your attention, and I'd welcome any collaboration ideas you have for extending this work in other directions. Thank you.
So, Dr. Coen, I have 3 questions that have come in this way for you. So the first one was about halfway through your talk, and so it said your insightful models and visualizations seem primarily to be done after the fact. Of course, you got into prediction a little bit later, so I was wondering, well, it ends with what are the prospects for real-time forecasts that could be used to safely position firefighters. You got into a little bit of that later in your presentation. Did you want to add anything in terms of the prospects for prediction to the point that you could position the firefighters better?
Well, I almost felt embarrassing coming to supercomputing. I thought I might get booed off the stage because our chips are getting so fast and our problem is of a fixed size that I'm really looking at the exciting possibilities that we might be doing forecasts on personal devices. I don't know if that's completely inappropriate for this crowd, but it's another exciting direction. Nearly all of the fires can be done as a forecast on, very manageable computers. But, if in a research sense, these bigger problems are really still a supercomputing problem.
Yeah, that's great. The second one, you mentioned the aerial data, sensor data. Do you use data assimilations significantly to improve the quality of the simulations? And I think in a way, data assimilation is a term that is widely used in climate and weather. So.
In my field, numerical weather prediction, we use the term data assimilation. And I thought that certainly applies to what we're doing here, but what I'm thinking is a little broader, a much closer relationship between model and data. I mean, in some sense, in some cases, the data might tell us, might guide our modeling, and sometimes our modeling, we're looking at applications, how that could guide us to look closer into the data. So a little more broader than we use it traditionally in numerical weather prediction, where we take the data and we put it in the model and use it.
Right, very nice. Okay, the last question is, wildland fires are rare events, and we don't expect explicit predictions for onset any more than we do for earthquakes. However, there are systematic campaigns to characterize likelihoods of onset as a function of moisture history, for example, current weather, so to indicate, the likelihood, with some error bars.
What I've been discussing is once a fire occurs, where will it spread? But there's other questions of likelihood of fires, fire risk. That's kind of a separate set of calculations involving current conditions, and it's sort of a different problem.
Okay.
Is that what it, like fire, yeah.
Right. Are there any other questions? Let's see, setups? You can come here.
The question is regarding the predictability. It seemed to me that there are 3 things. One is the model complexity, the local topography of where the fire is, and the third is local weather variations like a lightning strike or a moisture content. So are these the 3 things that stops? I mean,
the fire environment, the 3 primary variables in what we call the fire environment are the weather, notably the winds, the fuel, which is how much of it, how it's distributed, but also how moist it is, and the local terrain slope.
So my question is, in a way, the model complexity can be addressed with more and more accurate sensor data being part of the model. The local variations of the weather can be anticipated too, if you have historic patterns, right?
To some extent, but climatology will get you so far, but really not farther for a specific event, and not at this scale.
I mean, I was coming to my question of what was limiting from the total predictability. Is it the local topography, or is it the weather variations, or is it the model?
Oh, that's a good question. I always get the foresters mad because they try to interpret everything that the fire does in terms of fuel, because that's where their experience was. But with all my experience with this, the uncertainty in the fire evolution really comes from the weather, particularly the large-scale conditions, and how that not interpolates, but how that scales down to local factors. I think that's where a lot of the uncertainty is, and that's where our work has to be in improving it for the future.
Okay, well, thank you very much for a fascinating talk.
Thank you.